In this video, we'll be going through the 2018 Mechanical Systems paper. Question 1. The Electron rocket, developed by New Zealand company Rocket Lab, has begun commercial launches of satellites from Mahia Peninsula in Hawke's Bay. The rocket can carry a satellite of mass 1.5 times 10 to the 2 kgs to a stable circular orbit of 5 times 10 to the 5 meters above the Earth's surface. Show that the force due to gravity on the satellite in this orbit is 1,270 newtons. And so on your formula sheet you'll find the equation of gravity to look like this, where we just need to plug in our numbers. And instead of 1.5 times 10 to the 2 here, I'm just going to write that as 150 kgs. I don't know why we'd have such a small power there. And our large M is of course the mass of the Earth up there. And the radius down here is going to be the orbit of the satellite, which is above Earth's surface, but we also need to account for the actual radius of the Earth. Let me draw a quick diagram. So in our gravity equation, our radius is from the center of masses, and so we need to account for the radius of the Earth plus the distance that the satellite is above the surface. And that indeed gives me 1,270 newtons to 3 significant figures. The rocket, the satellite, and any space debris at the same altitude in stable circular orbits will all travel at the same speed. Show that this is always true by deriving the formula for orbital velocity, which we see right here, and use this to determine the orbital velocity of the satellite. So the first step in deriving this particular equation is to recognize that the satellite is in circular motion, so we have a centripetal force, and that centripetal force is provided entirely by gravity. We know the equations for each. We can now simplify this by dividing mass out and also multiplying both sides by r, which will cancel out the divide r here, and the square power there. And now we just need to square root both sides. And we've ended up with the equation that we want to find up there. So now, given that we know all of these things, we know the big M, which is the mass of the Earth, we know the radius, which is the radius of the Earth plus the orbit, we can now just plug those numbers in. Which gives me 7,610 meters per second to 3 significant figures. A 20 kg piece of space debris is traveling at the same altitude and speed as the satellite, but in a direction that is 90 degrees to the satellite's velocity. At the moment shown in the diagram below, the debris and the satellite are 1.08 times 10 to the 4 meters apart. Calculate the distance between the center of mass of the system and the satellite. So the equation for the center of mass that you're given on your formula sheet looks like this. So given that we're wanting to calculate the distance between the center of mass and the satellite, we'll make our x equals 0 here. And so if we imagine that our center of mass is something like here, our XCOM is going to be this here, which is what we're trying to find. We can make our M1 our satellite, which means that our X1 is going to be 0 because the satellite is at our X equals 0 that we have defined. We of course now make our debris M2, and our X2 is going to be this total distance here. As for the masses, the mass of our space debris is 20 kilograms, and the mass of our satellite, I believe we were given that up here, is 150 kilograms. which means we have everything we need to do this here equation. Bearing in mind that because our x1 is 0, we can ignore this term here. And that gives me 1,270 meters to 3 significant figures. Describe the motion of the center of mass of the system as the debris and satellite continue to move along their paths. Justify your response. And so let's look back at our diagram. So we can look at our center of mass here, and given that there are no external forces, the motion of the center of mass is not going to change. And the motion of the center of mass is going to be something like in that direction there. So it's just going to travel along this path and will even continue to do so if these two objects happen to collide. Now, there is, of course, the elephant in the room external force, which is gravity. But gravity here is acting perpendicular to all of our velocities. And it's also acting equally on the entire system, which means it's not going to affect the motion of the debris, the satellite, or the center of mass relative to the system, relative to each other. So we can eliminate that from our discussion. There are no external forces acting in the horizontal plane. The motion of the center of mass, therefore, will remain constant. The debris collides and becomes embedded in the satellite. Calculate the speed and direction relative to the initial direction of the satellite and embedded debris. And so let's first write down up here what we know. We know that the velocity of the satellite initially is 7610 meters per second, and that the velocity of the debris initially is the same as it says above. The caveat is that they are of course traveling at 90 degrees. And so if we consider the momentum of our debris, so we'll call that PD, plus the momentum of our satellite, they combine to give us our total momentum, which, since these two embed in each other and stick together, is going to be the momentum of them after the collision takes place. And so that will be the source of our information for our speed and indeed the direction. And so the angle that we're looking for, so we're looking for the direction relative to the initial direction of the satellite, so we're wanting to know the angle between the total momentum and the satellite, which is this angle here, and we'll call that theta as we like to do. And so this, of course, is our right angle. And so, surprise, surprise, we're left with a right-angled triangle, as we so often are with high school physics. And so we can use a bit of Pythagoras to find our p total, which we know that this squared plus this squared square rooted will give us that. And then we can use a bit of SOHCAHTOA to find our angle. Replacing our momentums with mass times velocity. Our p total is just the combined mass times the total velocity that we're trying to find. So if we just divide both sides by this here in brackets, we'll find our velocity. Putting in our numbers. Which gives me 6,770 meters per second to 3 significant figures. Now we just need to find our angle. To do that, we can look at our triangle here and use the relationship that tan of our angle is going to equal our opposite. Our opposite is our PD divided by our adjacent. Our adjacent in this case is our PS. We can solve this for angle by taking the inverse tan of both sides, substituting mass times velocity for our momentums. And now, since our VD is actually equal to vs, they're traveling at the same velocity, we can actually just cancel this out and save us a bit of calculating. So let's put in our numbers. And that gives me 7.60 degrees to 3 significant figures. Question 2. Whether satellites can be launched into orbits that circle around the north and south poles. This enables the satellite's camera to view the whole Earth's surface as the Earth spins underneath. The orbital period of a typical weather satellite is 101 minutes. Show that in order to keep the camera pointed towards the Earth's surface, the satellite must spin at an angular velocity of 1.04 times 10 to the minus 3 radians per second. And so if I fill in our grey space here with an appropriate diagram, let's draw the Earth and our weather satellite. Now the satellite's camera wants to be pointing towards the Earth. And so as it goes around the Earth, the satellite's camera is going to need to point in these directions, always towards the Earth. And so what I'm really getting at here is that the period of rotation of the satellite, so that its camera is always pointing towards the Earth, is indeed the same as our 101 minutes here. And so on your formula sheet, you'll find this equation here, that the angular velocity is the change in angular displacement over some duration. Now for one full rotation, that's going to be 2 pi. And our duration is our 101 minutes, which is 101 times 60 seconds, as we want this value in seconds, which indeed gives me 1.04 times 10 to the minus 3 radians per second. This angular velocity is achieved by firing two 5-Newton thrusters attached on opposite sides of the satellite's 1.60 meter diameter. Explain why 2 thrusters must be used rather than simply one on one side of the satellite with double the thrust force. So let me do a bit of a diagram right in this space. I'll rub it out when I'm done. So if we just had one thruster here, now, sure, we are going to get some rotation as a result of this, since we have an unbalanced torque, but the problem is we also have an unbalanced force. And so, since we want to rotate the satellite but not move it in its orbit or move it in an unstable orbit, we definitely do not want a net force. The solution is, of course, to put a thruster on the opposite side in the opposite direction. If we do that, not only do we have our unbalanced torques, which we want, but we have a force up here and we have a force going down here, which cancel each other out, so we have an unbalanced torque and a zero net force, meaning our satellite isn't going to plummet into the Earth. So let me try express that in words. We want an unbalanced torque, but not an unbalanced force. Having a thruster on either side means their torques are able to add and their forces are able to cancel. The thrusters are fired for a 6.48 times 10 to the minus 3 seconds to set the satellite rotating at the required angular velocity. Show that the rotational inertia of the satellite is 50 kg meters square. So to find the rotational inertia, we can use the equation that the torque is equal to the inertia times the rotational acceleration. Problem is, we don't know the torque or the rotational acceleration. So to find the torque, we know that the torque is equal to force times distance. And so our force, we have two 5-Newton thrusters, so our force is going to be 10 newtons, and our distance is going to be 0.8 meters, which gives me 8 newtons. Now to find our angular acceleration, we can use the following rotational kinematic equation. Since we know that the initial rotational velocity is 0, we're given the final above, And we know the time because we're given it right here. So let's now solve this equation for angular acceleration, knowing of course that our omega I can just disappear because it's 0. So I can do that by dividing both sides by t, and I'll switch the sides around to get our angular acceleration over here. Putting our numbers in, and that gives me 0.160 seconds to 3 significant figures. Over to our equation over here. We can solve this for inertia by dividing both sides by angular acceleration. And now we just need to put our numbers in. And I just noticed that I wrote this here, Newton meters is the correct unit there, which gives me precisely 50, and is exactly what we're trying to show. Instead of using two thrusters to adjust the angular velocity of a satellite, it is often preferable to use a reaction wheel system. When the wheel begins to turn in one direction, the satellite will turn in the opposite direction. The wheel is solid and has a rotational inertia given by this equation here. The radius of the wheel is 0.2 meters, and the mass of the wheel is 5 kgs. Calculate the angular velocity of the wheel required to keep the camera pointed at the Earth. State any assumptions. And so how this works is that you give the wheel some amount of angular momentum, and in turn impart an equal amount of angular momentum to the satellite. So we'll start with this statement here, and we'll work our way down. And our assumption here is that there are no external torques, such that we can assume that angular momentum is conserved. Angular momentum is just the inertia times angular velocity. And so we know the angular velocity of the satellite. We've used it a couple times. We also found the rotational inertia. And the rotational inertia of our wheel can be given by this equation here, which is going to make things a little bit messier, but we'll deal with that in a moment. So let's first solve this for our angular velocity of our wheel. And now let's substitute our equation here. Since we know all of these values, we can just put our numbers in, which gives me precisely 0.52 radians per second. Question 3. When astronauts return to Earth, a spring under their seat reduces the force during the landing. The astronaut's kinetic energy is converted to spring potential energy as the spring is compressed. If friction is negligible, this will set the astronaut into simple harmonic motion. State the conditions required for the astronaut's motion to be considered simple harmonic motion, which is just a stock standard answer and is a question that is asked in, almost every mechanical systems exam. Restoring force must be towards equilibrium and proportional to the displacement. During a landing, an astronaut and seat had a combined mass of 80 kgs and were set into a simple harmonic motion with an amplitude of 0.15 meters and a period of 0.940 seconds. Determine the spring constant of the spring and also the amount of energy, but we'll get to that in a moment. And so the period for a spring mass system is given by this equation here, which is on your formula sheet. If we divide both sides by 2 pi and then square both sides, we get this. And now if we multiply both sides by k and then divide by this side here, we can solve for our k and get this. Putting our numbers in, which gives me 3,570 newtons per meter to 3 significant figures. As for the amount of energy stored, we can find that using this equation on your formula sheet. where our x is just our amplitude here. Putting our numbers in gives me 40.2 joules to 3 significant figures. Using a reference circle or otherwise, determine the velocity of the astronaut when the astronaut is 0.1 meters above the equilibrium position. Assume the motion is undamped. And so if we take our displacement as being in this direction here, our phasor, which is moving counterclockwise as they conventionally do, will look something like this, where our displacement here is our 0.1 meters. Our amplitude, which we were given up here, is 0.15 meters. And what I'm interested in is this angle here. Let me explain why. So we have our displacement, which is given by this equation here. I'm using the sine one since our spring we're assuming is starting from 0 displacement. Our velocity, therefore, is going to look like this, which is also on your formula sheet. Now, given that angular velocity is just angular displacement over time, that means that angle is equal to omega t, which means that we can replace our omega t here with just our angle, which is why we're so interested in it. Now, as for our omega, we can find it knowing that our period is 0.94 seconds. Since we know that our omega is 2 pi f, which is given on your formula sheet, we know that f is equal to 1 over t, which means this is also 2 pi divided by t. If we put our number in, I get 6.68 radians per second. So that's our all-important angular velocity. So, knowing that we now have our angular velocity, we know our amplitude, we just need to find our angle, which will let us calculate our velocity. And now to find our angle, we can look at this triangle here and use a bit of SOHCAHTOA. We have our opposite here, we have our hypotenuse, which means that we are going to use the SOH relationship, which is that sine of our angle is equal to our opposite, which is 0.1, divided by our hypotenuse, which is 0.15. Taking the inverse sine of both sides allows us to solve, which gives me 0.730 radians to 3 significant figures. Now we can use our equation that the velocity is a omega cosine angle, where we can just plug our numbers in, which gives me 0.747 meters per second to 3 significant figures. The motion of the astronaut is quickly brought to rest by a damping system on the spring. Damped harmonic motion can be modeled in the laboratory with a mass, spring, and a beaker of water as shown. Discuss how damping will affect the amplitude and period of the harmonic motion of the mass on the spring. Your discussion should include a description of what is meant by damping, a description of the damping force in the laboratory model and how this will impact the motion, and a sketch of the graph of position of the mass versus time, starting at the moment the mass is released from the maximum downward displacement. So let's address these in order then. The amplitude will gradually decrease. Now, as for the period will not change. Now, to describe what is meant by damping. Damping describes the loss of energy to a simple harmonic system. Now it wants a description of the damping force in the laboratory model. And so as we can see here, our model damps the system by having this here apparatus in the liquid, and we're going to get a friction force which is going to oppose the motion of the mass both upwards and downwards. The lab model has a surface submerged in water. This surface will experience friction forces that oppose its motion and that of the spring mass system. And so our last point, it wants a sketch of the graph of position of the mass versus time, starting at the moment the mass is released from the maximum downward displacement. So let's do that. So our maximum downward displacement is going to be here. And so obviously I'm going to have the amplitude decreasing over time, which means it's going to go within, let's say, these bounds here. But what I want to make sure of is that the period remains the same. That's one thing that the examiner will be looking for. So let's try that. And we're done.